The event code is not working. Give me 1 minute. Let me see what's wrong.
I think it's a small R. That might be it.
Oh, is it case sensitive? Yeah, it might be why.
All right, to everybody that just hopped in recently, we're just going to be waiting a few more minutes before we get started. Thanks for being on time.
For those who got here late, the event code is Ronde with a lowercase r.
All right, it seems like we're pretty close to 7:05, so let's go ahead and get started. Big thank you to everybody that's here. This is ACM AI Apply ML workshop number 3, and super excited to have you guys here for the 3rd edition of our workshop. So the first workshop, we went over pandas and just data cleaning and how to get your data prepped for your machine learning model. We then switched over to talking a little bit about models during the second week, and we talked about logistic regression. And then today we're going to be going into the big fish, which is neural networks. Now, you guys have all probably heard a lot about neural networks, probably heard a lot about deep learning, heard all the buzzwords, heard all the hype. And you guys are probably pretty curious on, what exactly a neural network is and how exactly it works. So we're going to be going over a high-level overview of what exactly a neural network is, and then we'll get into the notebook where we will be coding up a neural network and seeing how it performs. So let's get started. Oh, did you guys just have the CS31 midterm today? First one. I remember that. I did. Oh boy. Yeah, I remember I got a B+ in CS31, and I thought the world was ending because, I didn't get an A in my first CS class. Am I cut out for this? But, even if you do badly, don't worry about it. It's just one class, and, you'll be chilling. Anyway, let's get back to our neural networks. So we talked about logistic regression last week. We briefly went over linear regression last week as well. And the common factor between those two functions is that oftentimes they're too simple. If you guys remember last week, we had a hypothesis function, which was a linear combination of the weights like W1x1 plus W2x2 plus W3x3 all the way to Wn times xn, and then that'll give you some sort of output. Now, if you guys remember from last week, that was a linear function, which meant that we could really only map linear relationships or look for a linear decision boundary. If we have anything more complex, whether that's a polynomial function, like a quadratic or cubic function, or anything more complex than linear, then logistic and linear regression are just not going to be able to handle that, right? And oftentimes in the real world, we have very, very complex functions that we want to model. Like, for example, companies like Citadel use neural networks, deep learning to predict what the best time to buy a stock is. Medical imaging companies will take images and put them into a neural network and then tell you whether that image is X or that image is Y. So oftentimes we want to model stuff that's a lot more complicated than just a linear function. And that's the beauty of a neural network. It's pretty much as complex as you want it to be. So I think a lot of times when we're talking about neural networks, we start off by talking about the human brain and what the relationship between the two is. A lot of times a neural network is introduced as similar to a human brain because we're trying to mimic the intelligence of a human brain. If you think about the way a human brain works, it takes in a lot of inputs and it gives you an output, right? If you haven't eaten in a while, it's like maybe 6 o'clock, you haven't eaten dinner yet, and then you get the input from your stomach that is grumbling. You get the input from your nose that you smell dinner, and your output is that you become hungry. So you have an input and an output, right? So a neural network works in a similar way. We have a bunch of inputs, and then we map that to some output. Awesome. So like I was saying, neural network is often compared a lot to a biological neuron, as in like a human brain, right? And a human brain is made up of a whole lot of biological neurons. And these biological neurons, yep, says it right on the slide. They'll take electric signals from surrounding neurons and then pass them forward to more neurons. And then eventually these neurons will pass them on to other neurons before we get some sort of output, right? And that's kind of what we're trying to replicate here. A neural net, like every unit of a neural network will like do something to the data and then pass it forward, and then something else will be done to the data. That'll get passed forward again until we get to the end where we get our output. So let's just look at on the next slide what the units of a neural network are actually made of. So let's talk about the artificial neuron, right? So what we're essentially trying to do is, I guess, in a way, mimic what's happening with that biological neuron, because we're trying to take inputs, do something to them, and then pass them on, and then do something to them again, and then pass them on again, right? So neural networks are essentially made up of all of these small units called an artificial neuron. Now let's just take a quick look at that diagram that's to our left, to our right here. So if you guys remember from last week, x0 through xm are our different weights, right? These weights are, or they're actually, excuse me, they're actually our different features. And these features from the Titanic data set were, price of ticket, or, where you're sitting in the cabin, things like that. And then the W's you see here are our different weights. And we'll essentially take a linear combination of all of these features and all of these weights, and then get some sort of output in the neuron. Now, this sounds pretty similar to what we did last week. So you guys are probably wondering, all right, like what's the difference between what we did here and what we did last week? So the difference here is that in an actual neural network, we're going to stack a whole lot of these units on top of each other in order to create that neural network. So, yep, Varun's on the next slide now. So just looking at this, every single one of those circles is essentially an artificial neuron, like the one you saw on the last slide. So on the left side here, we have all of our weights. And then in the middle, you have a layer of artificial neurons. And then on the right side, you have your output. So what we're looking at here right now is pretty much the simplest neural network of all time. We only have one layer in the middle of artificial neurons. On the right side, we have our output, and on the left side, we have our features or our inputs. So what's going to happen here is we just saw on the previous slide that every neuron will take in all the features, do some computation, and pass it forward. Now, instead of just having one neuron, we have 4 neurons. So each of these 4 neurons is going to take in all of our inputs from x1 to x3, do something to them, put them through something that's called an activation function, and then feed them forward to the right side here to get our output. So at a very high level, that's what we're doing. We're taking all of our features, putting them into a stack of a bunch of neurons, and then feeding that forward to get our output. So yeah, you see it right here on the slide. On the left side, we have our input layer. In the middle, we have our hidden layer, and on the right side, we have our output layer. So yeah, I think that's really generally a really high overview. So I'll hand it off to Varun now to talk about what exactly happens when we stack up those artificial neurons together.
Yeah, so like Harsh mentioned, a simple neural network is essentially combining a bunch of different logistic regressions. It's not exactly like that, but that's how you can think of it. So like you can see in this diagram, like Harsh mentioned, you have a bunch of features, and if you weight them all together, you get one output here, which is very similar to what we got in logistic regression. But this time what we do is we simply repeat that process one more step. So let's say instead of having just one logistic regression, we do maybe 10 different logistic regressions, and then finally take the weight all those logistic regressions again, and finally make a prediction. And you can see that each neuron carries a different set of weights. So while every neuron in the same layer gets the same input, it's going to weight the input differently from other layers in the neuron, and then eventually pass it forward to the next layer. And you can see that there's no reason why you should create just one layer. After you created one, you can just create maybe say even 100 layers. So what that means is essentially you have your input features. You map it to maybe 5 different logistic regressions. Now the output of those 5 logistic regressions will become the input for a next layer of logistic regressions. And you can keep going deeper and deeper and so on. And the reason we do that is it's been observed in a lot of different settings that when you make your neural networks a lot bigger, with a lot more weights, with a lot more layers, it tends to perform a lot better. And in fact, a lot of the popular machine learning models that you see today are often based on extremely, extremely large deep neural networks. So for example, if it's used in self-driving vehicles, the primary technology used today is deep learning. It's also used in several computer tasks. It's used in the GPT-3 model released by OpenAI that you might have heard. It's also used in natural language processing and so on. There are also different kinds of neural networks. We won't be going into that today, but that's just to help you understand that neural networks have a wide variety of applications, and they offer you a lot of flexibility to carry out a lot of different useful tasks. So yeah. Now let's go into intuitively why we try to create layer after layer. So let's say a neural network has to identify whether a picture is of a cat or a dog, right? Does anyone want to take a stab at how you think humans judge whether a picture is a cat or dog? You can drop the answer in the chat or just unmute yourself. How do you think that when we see a picture, what goes on in our brains, and how do we decide whether a picture is of a cat or a dog? So it might be some particular distinguishing feature, or so I guess, for example, you could say that maybe cats have a certain kind of ears, or dogs have a certain kind of nose, and that's how you make the distinction. So how do you think a neural network would try to make the same kind of guess? And actually, let's just stop for a second. Does anyone have any questions about what we've covered so far? I know that's quite a lot of information, moving from logistic regression to neural networks. So if anyone has any questions right now, please let me know.
Yeah, let's do a quick just 1 through 5 on high level overview. Do you understand what is happening with the neural network? Just if you could drop that in the chat really quick. Cool. Scene of 3, scene of 4, scene of 3. Cool. So from the guys that are putting in 3s and I guess the guys that are putting in 4s, where is your confusion? You know, what part of it is a little bit unclear to you? And if you don't know what you don't understand, that's okay too, because this stuff is pretty complex. If you could just drop that in the chat for us, that'd be great. Okay, yeah, let's just keep going then. Good point, Jacob.
Cool. Yeah, it definitely does take a little bit of getting used to. Like we keep saying every time, the only way it really sinks in is if you spend a lot of time thinking about it and just playing around with some of the code. So yeah, there is definitely a learning curve involved. So don't worry at all if it doesn't completely make sense. Hopefully it will very soon. So right now, I guess the most important thing to keep in mind is that, like in logistic regression, you start off with just your input, which is your input data, and that input data gets fed into maybe 5 or 10 different neurons. And now the abstract jump in logic here is that the outputs from the first layer become somewhat inputs for the next layer, and you can essentially just keep repeating that process over and over again. So maybe the first layer learns a little something about the pictures, and using the weights of the first layer tells the second layer, well, I learned a little bit from these images. Why don't you try and see if you can learn a little bit more? And the intuitive way you can think about it is that when we look at a picture of a cat or a dog, we don't really know what's happening. We just know it's a cat or a dog, right? But it's not that easy for a computer to do the same thing. So maybe after the first layer of the neural network somewhat has an understanding of, okay, maybe there are edges in this picture in the top left region, the bottom right region, and so on. Maybe after the second layer passes on its inputs to the third layer, the neural network at this stage understands, okay, maybe these edges form a year. Maybe as it goes from the second to third layer, it says, okay, I think that this particular region of the image has some eyes. And then finally, maybe the last layer says something like, okay, I think these eyes resemble a cat more than a dog. Now, that's of course not exactly what goes on, but you can think of it as you keep adding layers to your neural network, it starts picking up some kind of features from the image layer by layer, and eventually it's able to use that information to make a prediction on what it's able to make a prediction on what class an image belongs to. Yeah, there definitely someone said there's a crash course on AI on YouTube that gives a really good intro, and I definitely encourage you all to go to YouTube and check it out. I think the popular YouTuber 3Blue1Brown also has a few videos on neural nets. It's very helpful to visualize and understand what exactly is happening. So after this workshop, I encourage you to get everyone to check this out. And yeah, I hope that you guys have a high level understanding of what exactly a neural net is doing. So once again, 1 to 5, just drop it in the chat. How comfortable are you guys with an overall understanding of what a neural network is like. So we have one question here. How many layers can a network have? So that really depends on you. For today, for example, we'll be sticking with smaller networks just to get started, 2 to 3 layers. But in practical applications, you might see that with huge amounts of data, it might be necessary to have maybe even hundreds of layers. And what determines its dimensions? So now, typically, if you have more features, you want to have more weights. And in the intermediate layers, it's kind of up to you. It depends on the model architecture. In fact, there's a lot of research that goes into how you determine what the appropriate number of layers and weights should be, depending on your use case. Maybe a computer vision task requires something different from natural language processing. So that determines whether you should have maybe 5 neurons in your hidden layer, or 20, or even 1,000. That being said, the last layer is sort of your output layer. So that depends on what task you're doing. So let's say you want to determine whether something is like a cat, dog, or a bird. Then at the end, you'll only have 3 outputs, maybe a probability for each class. Maybe the last output says is the 0.7 probability it's a cat, 0.2 it's a dog, and 0.1 that it's a bird. So your input dimension is fixed because that depends on the data that you have. Your output dimension is fixed because eventually you want to predict maybe between 2 classes, 3 classes, and so on. But in between the model architecture, that depends on your use case and how you optimize it. So we have another function. How does the computer optimize the resulting function? Is it also through gradient descent? Good question once again. It does use gradient descent to determine the weights, similar to what happened in logistic regression. But now, if some of you are interested in reading about that in more detail, it's the weights are determined through a process called backpropagation, which we won't be going through in this workshop. But if some of you are familiar with calculus, then it's essentially like using the chain rule over and over again to get the derivatives with respect to every weight and constantly keep updating the weights. So yeah, there are a lot of optimization techniques as well. That's another hot area of research to determine the best way of optimizing a neural network to ensure that it's making good predictions and so on.
Yep. Actually, in I guess research and production ML, the optimizer you see most often in neural networks is something called Atom, which is kind of a more advanced optimizer that uses a form of gradient descent, but has a few more wrinkles thrown in. So gradient descent is kind of the most basic version of optimization, and then there's like more advanced versions of optimization called like RMS prep and Atom and things like that. So keep in mind that usually there's a lot of different changes that you can make to neural networks, whether that's, the number of layers or like the dimensions, as Cameron said, or, what the optimizer is. But for this workshop, we'll be going through the most vanilla basic kind of neural network, just to start with the basics.
Cool. So let's go ahead. Yeah, so this is just basically a visual representation of what's kind of happening. You have your input layer, it produces the output for the second layer, and then that becomes the input again until you finally have an output. So one thing that we didn't discuss in detail was that you can have something called an activation function. Don't worry about that too much right now. Just like how we had this sigmoid function last time, after you move to a different layer, you apply the activation function before going to the next layer. That's just a technical detail that you don't need to worry about right now. And yeah, a typical convention is to call all the layers in between hidden layers because in some sense, it's a black box. So you just have your inputs, eventually you have an output. You don't always have to worry about what's happening inside. That's usually handled by the Python software or any machine learning software that you use. Right. And lastly, for anyone wondering why we bother with neural networks at all, The reason is that any continuous function can be modeled by some neural network. And so any kind of decision boundary that you want to learn, it's possible with a neural network. And that's the reason why we have so much flexibility with deep learning and neural networks. So yeah. This theorem does not talk about how you would learn the appropriate number of layers, the appropriate number of weights, and so on. This just says that there is some good network out there, and it's up to us to find the best algorithm to find that neural network in the appropriate weights.
Yep.
Right.
Varun, if I could just say a few more things before we jump to the yeah, right here. Cool. So yeah, I think this is probably one of the most important things we're going to talk about today, because what this says is that a neural network can learn anything, pretty much anything, as long as there's a way to map from A to B. A neural network can learn it. So, but of course, there are a few caveats here, right? If a neural network could learn anything, we'd just be, we'd pretty much already have everything solved. So, the caveats here are that to learn really, really complex functions, you need really, really big neural networks. The more complex a function is, the bigger a neural network has to be. For example, if we want to learn something simple or something like relatively simple, like telling the difference between like a black image versus a white image, the neural network is going to be relatively small. But if we want to do something really, really complex, like, predict a stock market price, or, predict how long it will take to get from point A to B, that's when the neural networks start getting really, really big and really, really massive. Now, the bigger a neural network is, the more data you need to train that neural network. If you don't have enough data to train a big neural network, that neural network's pretty much useless, because it's not going to be able to learn the function because there's not enough data. So that's like some that kind of leads into where some of the big bottlenecks in machine learning are. So for some of the most complex things that we're trying to do, there's often not enough data to train our neural networks, because we know we need such a massive neural network in order to learn the function. So yeah, that's all I wanted to say. Hopefully this little set of slides give you guys a good overview on what exactly a neural network is, and maybe give you guys a high level overview of what's happening behind the scenes. So let's jump into the code now. On the next slide, we have the tiny URL to get the Google Colab, as we always have. So, just like we always do, go to this link, download it, open up Colab on your local browser, and then upload this notebook to your Colab and open it up, and you should be good to go. And we'll give you guys a few minutes to do that.
So for everyone who hasn't been there in previous workshops, I'm just gonna do the same thing here.
By the way, if you weren't here at any of our previous workshops, meaning you weren't at workshop 1 or workshop 2, could you just drop a quick note in the chat? Feel free to just put it in the chat, or if you don't want to put it in the chat publicly, just send me a DM. So that way we have a count of, how many people are new and how many people were already here before. I think most of you guys are already here before. I mean, I see a lot of familiar faces or familiar names. So I just wanted to get a count. Exactly.
Right. So once again, just to recap, go to that link, download that file, go to Google Colab, click new, my bad. Go to Google Colab, go to file over here, and click on upload notebook. You can then choose a file. It should be in your downloads. Select workshop 3, hit open. And you should be good to go. Just drop a quick message in the chat once you guys have the notebook open, so that we know that we can proceed. We'll be waiting a couple of minutes that everyone is ready. Is anyone having any particular problem with opening up the notebook?
So for me, I can't download it from, like, there's like a little lock thing next. Oh, hold on. Yeah, I don't see the download icon on the side of the screen when I open up the.
Oh,
That's, let me check that out. See what's going on there.
Although
so the screen that's like this does not show up.
it does, but
There should be a download option somewhere here. So this one essentially.
yeah, it's, for me it has like a little. It just doesn't like look like the page is the same and it has the open with, but in the upper right hand corner it just has.
Are you logged in with your UCLA account?
Yeah.
Can you refresh the link and try again? I just changed the permissions.
Okay, sure. Huh. It might just.
Is anyone else having that same problem? Can you just drop a note in the chat just so we know if it's maybe a local problem or it's a universal problem? Huh. Are you logged into a Google account?
Yeah.
Man, this is super weird.
So can everyone else just drop a quick yes or no if you have the notebook open?
I think it worked. I think whatever you did for change when change permission got worked.
Awesome. Chilling.
Okay, cool.
Cool.
Seems like everyone. There's one no. Okay, never mind. Cool. So it seems like everyone has the notebook running, and this time we made sure that the data is easily accessible to even people who didn't come to our previous workshop. So this time we're going to be working with a new data set, one that's pretty much ready to use. No major cleaning of the data is required for this one, luckily. So we're just going to work with it directly and build a simple neural network. So if you guys run the first cell, the first one usually takes a little bit of time. Cool. So if you look at the columns in this data set, you have basically, so let's just discuss what the data set is first. So this is a blood transfusion data set. So essentially what this means is that a medical center has data about previous donations made. And the idea is that if you're scheduling a new blood drive, you essentially want to predict which people are most likely to donate blood again. And that's often needed because blood is often in shortage and you want to get people to donate. So maybe you want to target those people who are likely to donate again. And so typically on most people who donate blood, they have some sort of data. So one might be recency, when was the last time they donated blood? Frequency, how many times have they donated blood? Maybe in the past 2-3 years. Then I know this says monetary, but the next column is essentially what's the total amount of blood they've donated in their lifetime, and yeah, so for how many months have they been donating blood. And then finally, what we're trying to predict is whether that person donated blood in March 2007. So essentially, if we can build a model with this data, and let's say we're trying to build a prediction model for a blood drive in 2008, then we want to use this past data to predict which people are most likely to donate their blood again. So that's a brief overview of what this data set looks like. So are there any questions about that? Just drop a quick 1 to 5 if you have an overall understanding of what this data set is about. Cool. So let's go ahead. Now, last time, the last couple of workshops, we've been working primarily with pandas, data frames, and this time we'll be working with a library called NumPy. And NumPy is primarily a Python library that makes it a lot easier to work with data in the form of matrices. It makes matrix multiplication really easy. And you can also use it to build a lot of scikit machine learning models, just like with pandas. So it's if you're interested in data science and applied machine learning, NumPy is definitely something that you eventually need to learn. So hopefully this workshop will provide you a brief introduction to NumPy as well, in addition to building a simple neural network. So when you do data.to NumPy, it essentially converts the pandas data frame into a NumPy array. So if you run the cell, you see that essentially the data frame is now a matrix where you still have the first 4 columns are the feature variables. And the last column, which is a 1 or 0, is whether that person donated blood in March 2007. So the X would be the left portion of this data. The Y would just be the last column. And like we discussed last time, it's often a good idea to shuffle your data set. So I guess this is the first exercise for today. Google NumPy shuffle and try to figure out how exactly you can shuffle the data that you have. Yeah, shuffle the rows of the data essentially. So I'll give you guys a couple of minutes. Just literally search for NumPy shuffle and see if you can figure it out. It's just 1 line of code. So you essentially want to shuffle the rows of data. So we'll take a minute and let's see if you guys can figure it out. So if you Google something like NumPy shuffle array, you're gonna get this link. So it's always useful to just quickly Google what you want to do and see if there's any documentation for it. So if you see here, we have a very simple line of code that essentially shuffles the data for us. So I'm just going to go ahead and copy this line of code. Go back here, type this up, and know that our array is called data. So let's do this and go ahead and print the data once again. And if you notice here, once again, the last column remains, the last column is still whether or not a person donated blood. But you also have the rows in a different order. So for example, here the first row was 250, 12,598. Here it's 4,043. So the rows are clearly in a different order. So now I guess let's try printing out different parts of the data just to get familiar with NumPy array indexing. So if I wanted to print, say, the 7th row of the data, what I would do is I have my data and I want the 7th row, which is essentially the 6th row with NumPy indexing. So I'm just going to go ahead and say print data 6. And if I run this, I'm going to get 11, 1, 250, 11, 0. So this is the 7th row of the data set. Just want to take a quick pause. Is everyone following what we're doing here, or do you guys want me to go slower? Just let me know if you have any concerns in the chat. Now, similarly, you can also do something where if you want to print the second column of the data, what you would do is something like data, and then you say colon, which means you want all the rows, and then you say you want the second column, so 0, 1, so you would put 1 over here. And if you go ahead and print this, that's a little weird. Right, yeah, that is true. My bad. Yeah, sorry about that. Syntax always remains confusing. So if you want to print the second column of your data, what you need to do is you need to basically say, I want all the rows of the second column. So that's how you would get access to that data. Now the next step is if you want to print the last column of the data, NumPy has this quick trick that you can use where you can basically say print all the rows of the -1th column. And -1 here essentially just means the last column. And so similarly, if you do something like -2, then that would simply be the second last column. And that's quite convenient if you don't know how many columns there are. So know that doing -1 is simply the same thing as doing 4, because we know there are exactly 5 columns in this data. So that's just a quick trick that you can use with NumPy. And finally, okay, based on this, does anyone want to try putting in a line of code that prints the third element of the 5th row? Once again, I'm gonna wait for a minute for you guys to try this out. If you have an answer, feel free to drop it in the chat. If you don't want to send it to everyone, you can send it to just me privately. So what we want to do here is print the 5th row's third element. So essentially the third column of the 5th row. That's what we want to try to do. Right. So we have a couple of answers. So there's one common mistake that a lot of people make that's quite confusing at first is how do you know whether rows go first or whether columns come first? And the idea is that we have one correct answer in the chat. The idea is that first you want to get the exact row that you want. So if you want the 5th row, we would say something like data 4. And now we want third element in this row. So then you could do something like this. So you could do something like print data 4, 2, and this should work, right? And in fact, even if you do something like this, this should also work. Once again, you get 500. And yeah, not really sure when. Usually it doesn't matter whether you put rows and columns in with a comma or in separate brackets. Yeah, honestly, I'm not sure what the exact difference is. I think it usually works with both. Yeah, not really sure what happened before. Right. Okay, so lastly, let's try to figure out how exactly we would print all the columns in the data set except the first two. So we want to essentially skip over the first two columns and print the rest. So for this, what you would do is you would say that I do want all the rows because even in the last 3 columns, I want all the rows, but I don't want the first 2 columns. So I don't want columns 0 and column 1. So here I'm telling Python that I only want column 2 onwards. So if I do 2 colon, it says essentially give me all the columns from 2 onwards. So if I run this, I essentially get columns 2, 3, and 4 like I wanted. So this essentially gives you all the columns except for the first 2. Cool. So that's just some basic NumPy array slicing. It definitely, once again, it definitely takes a little bit of getting used to. It can get very confusing even if you've used it for a while. So this definitely requires a little bit of practice. But yeah, let's go ahead. Cool. So the next thing that we're gonna do is essentially split the data into training data, cross-validation data, and testing data. So what this essentially means is that, like we discussed last time, it's a good idea to split your data into training and testing. So that's because you can train your data on the training data and then evaluate your performance on unseen test data. The reason we also have cross-validation data in a lot of more complex models is that maybe we want to change some parameters of our model, right? Maybe we want to determine whether it's better to use 3 layers or 5 layers or 2 layers. Maybe it's better to have 5 neurons in a certain layer or 10 neurons in a certain layer. So in this case, what we do is we still train on the training data and then see whichever one does best on the cross-validation data. And then finally, use that information to determine the best model and still evaluate a performance on unseen test data. So that's the importance of cross-validation data. It essentially helps you figure out what the best parameters for your model are, but you still need a testing data set to ensure that you're finally reporting or evaluating your performance on completely new unseen data. Right. So are there any questions at this stage? I know that's quite a lot of information. Any confusions about what training, testing, or cross-validation data is, or anything like that? So we have a question here: which data is the final test set, testing or cross-validation? So that's a good question. So the final test, in some sense, is the data called testing data. So, like I mentioned before, you would train your model on the training data. Maybe you would build maybe 20 different models and train them all on the training data. Then see of those 20 models, which one does best on the cross-validation data. And whichever one does best, you say, okay, that's going to be my model. You pick that model. It's already been trained on the training data. And you use that to make predictions on the test data to see how you're doing. So the cross-validation data, in some sense, is an intermediate stage, basically to help you decide what the best model is. So that's what a cross-validation data is mainly for. It'll get clearer as we go down, where we experiment a little bit with some code. So based on the array slicing over here, let's try to basically split the train CV and testing data into train X, train Y, CVX, CVY, and so on. So the idea here is that train X has to have all the columns, has to have the first 4 columns, and train Y has to be simply the last column of ones and zeros. And similarly for CVX and CVY, it should just be CVX should be the first 4 columns of CV, and CVY should be the last column, and same for test. So let's see if you can come up with some short code that essentially does this for you. Each piece of code here is just one line, and it's essentially the same code over and over again. So just try to use the information that you have here to essentially split your data into X and Y. Once again, we'll take a quick minute to figure this out. If you have the solution, just drop it in the chat or send it to me directly. Either works. Right, so we'll just be waiting for 1 or 2 minutes to see if you can do this. In the chat, just drop a 1 to 5. 5 implying that you kind of get what needs to be done, and 1 that you're completely confused.
By the way, you guys probably remember from last week that we did our training and testing and splitting a little bit differently. We actually used a inbuilt function called like train test split in order to get that split. So we're doing a little bit differently this time just because we want to show you guys different ways of just interacting with data and doing things that are like pretty standard within machine learning. So there's always a couple different ways to do things, and we just want to cover as many of them as we can. Awesome, seeing a lot of 5s and 4s. That's great to see.
Cool. So does anyone want to take a stab at what the solution could be? Or it's completely fine if you're wrong. It is a little tricky to get right in the first try. Okay, so I guess let's go ahead in the interest of time and see what needs to be done. So here, what you would do is if you want to extract the first few columns of train X, what you say here is colon. So you want all the rows. And here you're saying that you want all the columns up to, but not including column, the 4th column. So this would include columns 0, 1, 2, 3. So the first 4 columns, essentially these 4 that you have here. And lastly, for train Y, we want to have just the last column. So exactly like what we did before, you would take all the rows and the -1th column. So that essentially means just take the last column. Just for clarity, I'm also going to say that this is the exact same thing as doing something like this. So extracting column number 4. The last column is column number 4, so this is the same thing. And you can do essentially the same thing over and over again. So here it would just be CV. Here it would be the last column of CV. For this, it would be test. Right. And so once again, for all of these, you can do, you can just extract the 4th column directly if the -1 is tripping you up. My bad. Right. So we have a couple of questions. So is the :4 exclusive? Yeah. So the :4 is exclusive in the sense that the 4th column will not be included. So you'll only have columns 0, 1, 2, 3. Which is kind of intuitive, because if you say up till 4, it basically means you want the first 4 columns. And we have another question that says, can we do for train X, can we do train : -1? Let's just put that in. And you can actually do that. So instead of this, if you do something like train : :1, what this means is pick all the rows and pick all the rows until the last one, so not including the last one. So yeah, this will give you an equivalent result. You can do either. So let's go ahead and run this cell. Oh, sorry, I forgot to run the previous cell. So just to go over this really quickly, what I'm trying to do here is I'm saying that roughly 60% of the data should be in train. Roughly 20%, so 80 minus 60, should go into cross-validation. And finally, the last 20% should go into test. So I'm doing a 60-20-20 split over here. And after that, I'm splitting it into train X and train Y. So are there any questions? Drop a 5 if you're with us so far, and let us know if you have any questions about what we've done until now. Cool. So I'm seeing a lot of 5s. So let's go ahead. Harsh, do you want to take over the standardizing data?
Yeah, so let's talk a little bit about scaling now. So we've already mentioned about how neural networks can pretty much learn anything as long as you toss enough data into your neural network. So by that logic, I feel like the natural line of thinking goes, okay, if a neural network can really learn anything, why should I really do anything to the data? Because the neural network will figure out any patterns that we already have. For example, let's say like one feature has a very, very big standard deviation, and another one has a small standard deviation. And then, one has like a very large mean, the other has a small mean. A neural network should be able to figure all those things out. And in reality, a neural network often is able to. But, because of the limitations we have on data, we don't have as much data available to us as we'd like. A data scientist or machine learning engineer always wants more data. So what we do instead is we try to simplify the problem for the neural network as much as we can. And in the process of simplifying, one of the things we do is scaling. So with scaling, what we do is we take every single feature that we have in our data set and we scale them to a standard scale. And what that standard scale is that every variance of every feature should be 1, and the mean of every feature should be 0, or if that's not possible, very close to 0. So essentially what we're doing is we're taking all of our features and then normally distributing them. So yep, like I was saying, we do this because we want to save as much work as we can for the neural network and make it as easy as possible for the neural network to interpret the data. This way, when every feature is normalized and has the same mean and same variance, the neural network can actually focus on the effects of the features on the output itself and not look for discrepancies between the features or think about like why certain features are large or small. So that's essentially what we do with this chunk of code here. So we're first gonna import the standard scalar and then say scalar equals standard scalar. Okay, so we've left this next little bit blank. So we'll give you guys about a minute or two. See if you can look up the documentation for a standard scalar and then figure out how to fit and transform, hint, hint, all of our data so that it has the same variance and the same mean. It should be super straightforward if you just look up the documentation for a standard scalar. We'll give you about a minute for that. So let's check in again at 8:04.
So it's pretty similar to scikit-learn, um, like we did last time. So the idea is that you first want to fit your scalar, and then you want your scalar to produce an output.
Okay, cool. Let's go over the answer. So it's pretty straightforward, very, very similar to even how we implement our models. So the first line, I guess I'll just read it out as Varun types it in, is scalar.fit train x. So that's pretty much fitting all of our train x data into the scalar. So in that step, the scalar is identifying like what the mean and the variance should be. And then in the transform step, which is the next line, that's when the scalar actually transforms the data and normalizes it. Awesome. If you want to do this all in one line, there's also another function called scalar.fit and transform. I think that's what it's called. And then you just put in train x and it'll do that for you as well. Okay, next thing. So we just scaled the training data, but we can't only scale the training data and not scale the testing data, right? So we also want to scale the cross-validation and testing data, but we're going to scale these according to the mean and the variance of the training data. Does anybody have any idea why we do that? Like why wouldn't we just scale the cross-validation and testing data with their own mean and variance? Why do we use the mean and variance of the training data?
Take a stab. It's completely fine if you're wrong.
Okay, well, All right, yeah. So the reason we do that is because of a concept I mentioned earlier, which is, I guess similar. It's similar to data leakage. We don't want the model to know anything about our testing data or our cross-validation data. And in the real world, when we get training data or when we get testing data, we also don't know anything about that data, right? So let's say we have some trained machine learning model and we want to make a prediction on something that comes in. We don't know anything about that, that new instance we just received. So because we don't really know anything about it and we don't have a set of it, we have to scale it and we have to normalize it based on the information we already have, which is the training data. That's why we do something similar here with the testing and cross-validation. We're technically not allowed to have any information on what's in the cross-validation set or what's in the testing set. That's why we use the information from the training data to scale those. So I guess quick exercise again. So very, very similar to what we just did. If you could scale the cross-validation and cross-validation and testing sets, I'll give you guys about a minute to do that.
Also, if you guys notice over here, so after we scaled the training data, if you look at the variance of every feature, it's all exactly 1 by construction. And if you look at the mean, well, it's in this form because of floating point errors. But if you see, it's -4 to the 10 raised to -17, 10 raised to -17. So it's all pretty much 0. Right. So do not scale the y column at all. Do not scale that. You would only scale CVX and test X. CVY would not be scaled at all. My bad. That is not what I meant. Thank you for catching that. Do not scale CVY.
Cool. Let's just go over the answer real quick then. Varun, if you have that, if you want to put that in. All right. So, yep, just quick changes there. And yep, that should do exactly what we want. So we're just using the scaler, which has already learned the mean and the variance of our training set to transform our cross-validation and our testing sets. Okay, that's all for scaling. Let me hand back to Varun, who will walk you guys through the neural network.
Cool. So yeah, I guess a quick observation. While the variances and means of the cross-validation and testing data are approximately 1 and 0, they're definitely not as accurate as this, which makes sense because the mean and the variance of the training data would be slightly different. But as long as it's somewhat in the same neighborhood, it's okay. Right. So I guess the next step is to basically just use like initialize our neural network model. So for this, we're going to use something called the MLP classifier, which I think stands for multi-layer perceptron. Now that's a fancy way of saying basically multi-layer linear logistic regression. And yeah, so what essentially means is like last time when we said, okay, here's a neural net. How do we initialize it with scikit-learn? So you want to essentially initialize this to something. Let's see if you guys can search for MLP classifier and figure out how exactly you would initialize this neural net. We can take a couple of minutes. So 1 to 5, does do you kind of get what we need to do over here? Just drop a quick number in the chat. Right. So this is very similar to what we did in the previous workshop, where we initialized a logistic regression model and then eventually fit that model and predicted on training and testing data. Right, so we have 5, 3, 4. Let's just wait a little bit before going ahead. So I understand what we have. We have a question here that says, I understand what we have to do, but I'm not sure what to write. No worries. So let's just go ahead and take a look at the solution. So what you would do is something like this. You would say neural net should be an MLP classifier, and we want the hidden layer sizes to be 5 and 3. So what this means is that you want to have 2 hidden layers, where the first hidden layer has 5 units, the next one has 3 units, and you want the random state to be 1. Don't worry about the random state at all. If you want, you can leave this out. This is just that all of us have consistent results. That's the only reason I left that in. And max hitter, honestly, you can make it even larger, just say 1,000. It just says try it at least 1,000 times so that the model eventually converges. So that's how you initialize your neural network model. So you basically just say that the first hidden layer should have 5 units, the next one should have 3. If you add more numbers here, you can make your neural network deeper and deeper. But for now, this should suit our purposes. So running this would initialize our neural network. I'm just going to drop this line of code in the chat so that you guys have access to it.
I got it, Varun. I'll put it in the chat. Oh, you got it. Cool.
Cool. So I guess the next step is to fit the model with the training data. Anyone want to take a guess at how you would do this? This is the exact same thing, the exact same line of code that we did with logistic regression last time. And that's the beauty of scikit-learn. The code's pretty much the same across a bunch of different machine learning models. So we want to fit the training data. Anyone want to take a stab at how you would fit the model with the training data?
Yep. Kyle got it exactly. Neural net.fit train X, comma, train Y.
Yep. So that's exactly what we're going to do. And now the cool thing about this is that we know that our neural network has a bunch of weights, right? It has a hidden layer of 5 units, then 3 units, and finally an output layer. And when you do fit, behind the scenes, the neural network automatically learns the best weights. You can see there are a lot of parameters that we could change. If you notice over here, there's something called solver equal to Adam. That's one of the optimization techniques that Harsh mentioned at the beginning of the workshop. There's also activation function that we briefly touched upon during the slides. So you can you can change a bunch of these factors to get a different model. But for now, this should be good enough. So I guess the next step is essentially predict on the training data and calculate the training accuracy. So once again, the code for this is exactly like how you would do it for logistic regression. Predicting and calculating the training accuracy, the code is pretty much the same. So this should be a memory test, if you can remember what we did from last time. If not, that's perfectly fine as well. You can Google MLP classifier and see how exactly you would predict on the training data and how you would get the accuracy. So once again, let's take a minute to think about that.
Yep, like Varun said, exactly the same as last time. Last time we did logistic regression.fit train X train Y. Now we're doing neural network.fit train X train Y. So in the same way, we made predictions using our logistic regression model. You can use the exact same syntax, just change logistic regression to neural network, and it should do the job for you.
So once again, 1 to 5. Does everyone have a good idea about what we need to do over here? Cool. So I see a bunch of 4s. If anyone wants to drop the answer in the chat, that's cool. Otherwise, we can go ahead in the interest of time. Right. So we have an answer in the chat, and I think that is correct, almost correct.
Yep, I think
Oh,
that
yeah,
looks good to me.
that looks good. So let's go ahead and take the answer from the chat. Oh wow, that's messy. Zoom chat really does need to be fixed. So just like last week, when you want to make a prediction using your neural network model, all you need to do is hit neural network.predict on train X. And when you want to get your accuracy, you just do metrics or accuracy underscore score with train Y and train Y pred. And we can go ahead and print the accuracy as well. Right. So here we see that we have a training accuracy of 79.9%. So what that means is where our model is able to correctly classify pretty much 80% of the data. And but obviously that's not good enough. We also need to know how it does on unseen data. So we're going to run essentially the same code over here and get the test prediction. The code's exactly the same, just change train to test. And let's see how it does. Cool. So if you look at this, the test accuracy over here is 74%. So it's a little lower than the training accuracy. And that's something you would expect, right? Because your model is not going to do as well on unseen data as on the data that it's trained on. So you would expect the test accuracy to be a little lower. Right. So that's pretty good, right? We have data that we have, our training accuracy is close to 80%. And we now have a neural network that can predict 74% of the data correctly on unseen data. So if we're launching a blood drive next year, we can reach out to we can reach out to the people that the model predicts yes on, and hopefully those are the people who are going to come back to the blood bank and donate more blood this year. So yeah, that's pretty cool. Now, is that all there is? I'm going to let Harsh take over this section and see what else we can do to improve our model.
Awesome. So right now we're at about 74% accuracy. Now that's pretty good considering we just took our data, threw it into a neural network, and saw how it did in just a little under half an hour. That's pretty good. But if we're actually gonna have production ML, it needs to be a lot better. I mean, you guys have probably all used Google Maps before, and when Google Maps makes a prediction for how long it'll take you to get there, it's usually accurate like down to the minute, right? So we want to improve our neural network in some way. Now, how can we do that? So Varun mentioned earlier that there's a lot of different things you can change about this neural network, right? Like we use the solver Atom, we can change that into something else. We had a certain configuration for the hidden layer sizes. I believe it was 5 and 3. We can change that as well. Things like learning rate, those are other things that can be changed. So all these small things that you can change about a neural network in order to, change its performance are called hyperparameters, right? So some examples of hyperparameters are, the number of layers we have, the number of neurons in each layer, how big the layer is, the learning rate, the way we optimize, whether that's gradient descent, whether that's Atom, or whether that's something else, how long we want to train. All of these different values are known as hyperparameters, and we can change these hyperparameters around to try and improve our model's performance. So, essentially what we want to do now is, play around with these parameters, see which combination of these hyperparameters gives us the best performance. And then, then we'll train on that and see how that does. So if you see that link right there, that will, or Varun, if you want to just click on that link for us. Yep, so this is up the scikit-learn documentation, and this will tell you what all the different hyperparameters are. So hidden layer sizes, that's a hyperparameter. Activation function, different types of solvers, and then there's some that we haven't really talked about, like a regularization parameter, things like that. So all of these different things are a ton of different hyperparameters that you can change to try to improve the model's performance. So now going back to our model now. So one good way to decide what the best hyperparameters are is by using, cross-validation and then seeing which hyperparameters perform best. There really isn't one set method of determining the best hyperparameters. Usually you just try different combinations until you get one that works. So, you kind of throw everything at the wall and see what sticks. And that's kind of what we're doing here. So we've made a few changes to our neural network. We've changed what the solver is. We've adjusted the hidden layer sizes a little bit. And we've also set a max iteration limit of 1,000. So let's run this and see what happens. Okay, so all of a sudden, our cross-validation accuracy is a lot better, right? We're getting 85% accuracy now. And all we did was change a few of the hyperparameters. Now, after this workshop ends, I encourage you guys to go back to this little chunk of code and play around with the different hyperparameters, dig through the documentation a little bit, see what the hyperparameters are, and then maybe try to change them and see, what different performance looks like. Like, look, Varun just changed another hyperparameter and, the accuracy changed. So this one's a little bit worse. Let's make our neural network a little bit bigger, maybe put 7, and our cross-validation accuracy gets better. So this is telling us that, okay, maybe we need a little bit, a bigger neural network. Let's add in another layer, oh, that didn't work. Maybe that's not the best thing to do. So this is just a big trial and error situation. Try out random things, see what works, and then, stick with that. So we're seeing that maybe a hidden layer size of maybe 6 or 7 is giving us, the best performance right now. Maybe changing our solver from LBFGS to Atom will give us better performance. In this case, no. So essentially what we're doing here is we're just trying stuff out and seeing what works and seeing what gives us the best performance. So if I remember correctly, our best performance so far has been with LBFGS and hidden layer size of 7, I think. I think 7 had better performance than a 5. So yeah, 86%. Let's roll with that and then see how that performs on the rest here. So we're going to take that neural net that we just defined, and okay, so it looks like our testing accuracy dropped a little bit. So maybe this isn't the best combination of hyperparameters to use, but there definitely is some combination out there that will give us good performance. It's just up to us with our time, our money, and our resources to try and find it, right? So, all right. Of course, it can be a little bit of a pain, to do what we're doing right now. What we're doing right now is we're just kind of throwing things at the wall and changing things individually and seeing what works. A more deterministic way of approaching this is to essentially try every combination and see which one is the best. And that's what we've done here. So if we look at this quadruple for loop that Varun has wrote, we'll see that we're pretty much cycling through the different number of neurons that we have, the number of layers we can have in our neural network, the different learning rates, as well as different solvers that we can use. And then from this, we're essentially taking we're going to save the configuration of the optimal solver, the optimal learning rate, the best number of neurons, and the best number of layers to have. So if we run this chunk of code, we're just going to run through all of the different combinations and save the one that worked the best for us. So Varun, if you want to run this, I have a feeling that this is going to take maybe a minute or so to run, I think. So.
Oh, my bad. So let's say maybe you want to search up to, I guess, 3 layers. So maybe you want to experiment with layers, with a neural network of layer 1, layer 2, layer 3. Maybe you want to allow a maximum of 6 neurons per layer. You can experiment with your learning rate. Maybe you can do 0.01, 0.001, 0.0001, and so on. Finally, I guess for solver, you could try either Atom, or you can try something like you can try some of the common ones out there. And once you're essentially saying, okay, I want to search across all these permutations and combinations. So yeah, what you can essentially do is that once you say, okay, I want to search for all combinations of up to 3 layers of neural networks, up to 6 neurons per each layer, experiment between 3 different learning rates, and maybe experiment between a couple of solvers.
Yep.
And then when you hit run, learning rates is not defined.
Yeah, you just got to choose the LR to learning rates and you should be good. Yeah, there you
go. Of course. These small typos are always a part of every model.
Every CS project, to be honest.
Yeah, so finally it seems like we've got it to work.
All right, so this is going to take some time to run because, if you do the math, we're training like what, 24, 30, like 90 something models, I think. 80, what was that? 6 times 3 times 2 times 3.
18, 54, 108.
108. Yeah, 100 something models. Quick math. All right.
So already that's pretty fast. We train 108 models in barely a few seconds.
And it looks like it's output our optimal configuration, which is one layer, two neurons, a pretty large learning rate, and then the LBFGS solver. So let's see how that actually performs. And let's look at the accuracy here. Wait, mine told me 25001 atom. You know, Kyle, that's a possibility. It's probably because we didn't set a random seed to standardize everything. So it's super possible that you get something a little bit different just because of the randomness associated with this. So it seems like using the parameters that we put in, the best we could do is a training accuracy of 81% and a testing accuracy of 72.7%. Just out of curiosity, Kyle, what was the training and testing accuracy that you got with the optimal combination that your code spit out? Kyle, you there? Okay. 77 and 75. So much better testing accuracy than what we got here. But yeah, what we're trying to do. Awesome. Yeah, I think the specific number isn't as important. What we're trying to do here is really just illustrate an idea of how to tune hyperparameters and how to search for the best combination of hyperparameters. So what we've done here is very brute force. We've just trained every single model and looked at what does the best. In real life, though, when you have hundreds of different hyperparameters and hundreds of different possibilities for what these hyperparameters could be, it's not always realistic to train every single model and then see which one did the best. So a lot of times you kind of just have to try randomly, try sparse things, just try different things out and see which combinations work best. I'm actually working so I'm actually on the projects team at ACM AI, and right now with the project we're doing, we're actually in the hyperparameter tuning stage. So we're just training models and throwing things at the wall and seeing what works. So this is an important part of every ML process. Cool. So essentially what we did here is something called a grid search. And there's actually a function in scikit-learn called grid search CV that will allow you to perform this hyperparameter tuning, without writing a bunch of for loops yourself. But we're going to leave that as a exercise to the viewer. If you're curious, I'd really encourage you guys to check that out and try to get that to work and see exactly what that code's doing. It's going to do something very, very similar to what we just did here above, but I'd really encourage you to work it out yourself and see exactly what happens. So big congratulations to all you guys. You just built your first neural network, and not only that, you also tuned its hyperparameters. So, take some time after this workshop and play around with these hyperparameters some more. Maybe try some of the other solvers. Maybe increase the number of layers to more than what we had, and see if you can get better performance than what we got here. But Vern, if you have anything else?
Yeah, no, I think Harsh covered everything. I guess the most important thing is just play around with some of the values over here. Maybe search across more learning rates, more neurons, see if you can come up with a better model. The theory is one part, so understanding how a neural network works. But after that, in the hyperparameter tuning stage, that's a little more qualitative. It depends on your particular use case, how large your data set is, and whether it's feasible to search across many different hyperparameters. So just get an intuitive feel for how you can get better results by changing these hyperparameters and see where that takes you.
Yep. So yeah, with that, thank you guys so much for coming out to our workshop again. Looks like we had 13 people here today, and I'm recognizing a ton of your guys' names, which means you guys have been coming out to our first workshop and our second workshop and this third one. So big thank you to you guys for sticking through our 3 workshops here. And we'll have another one for you guys next week. Super excited for that. If you get a chance, please fill out that feedback form. We've been reading through all the replies you guys have sent in through the last feedback forms. If you guys have any criticisms, that helps us a lot because that way we can improve the workshop. And if you just have some compliments about our workshop, if you really enjoyed it, please let us know that as well, because that really lifts our spirits and makes us feel good and lets us know that the hard work we put into the workshop, is really helping you guys out. So I think that's all we have today. We're going to stick around for a few minutes just for some questions if you have any. If not, good luck with all your guys' midterms. I know it's week 4, so this is when midterm season really hits. And good luck with that. And we'll see you guys next week. Thanks, guys. Love seeing all the thank yous in the chat. Thanks so much, guys. Really appreciate you guys coming out.
See you next week.
Yep. See you guys next week. Fill out that feedback form. All right. Do you want to stop the recording, Varun?
Yeah.